Alright, hello everyone and welcome back. So in this video, let's discuss about the midpoint rule. So we want to approximate this integral using the midpoint rule, okay? Or we want to approximate the area in this region using the midpoint rule. Alright, where do we start? Well, we start with the main interval. So we draw the main interval, so it's going from A to B. And let's say we need to use n number of rectangles. So what we are going to do first is we are going to find the width. Width can be found using the formula b minus a over n, right? And we divide this big interval into small sub-intervals, right? Equally spaced small sub-intervals. I'm not a good artist, okay? All right. Now, however, let's label them. So let's say this a node is x node, and this is x1, this is x2, and so on, and this is xn. Okay, fantastic. Now let's mark them on our graph. So these are the sub intervals. Fantastic. All right, now the midpoint method is that what you do is you use the midpoint of each sub-interval to construct the length of the rectangles, height of the rectangles, okay? So what we do is first we mark the midpoint of each sub-interval. Alright, so likewise I find the midpoint of each sub-interval, the middle point, okay? And then connect the middle point with the graph, like this. So once you connect that, alright, make sure you form the rectangles, and then there you go, you get the midpoint approximation, okay? Rectangles using the midpoint of each sub-intervals. Alright, so let's try to come up with a formula for this. Fantastic. Now what we are going to do is, we know, as you know, we have to find the midpoint of each sub-interval, right? So let's do that. Let's list the main sub-intervals first, okay? So the main sub-intervals are x0 to x1, that's the first sub-interval. Second sub-interval x1 to x2, third sub-interval x2 to x3, and the list goes on, and the last sub-interval is xn minus 1 to xn. Fantastic. Now what you have to do is find the midpoint of each sub-interval. How can you do that? Think about it. Well, we can add the two endpoints and divide it by 2. So you get the midpoint of the first sub-interval, let's call it the x1 star, by adding the two endpoints and dividing it by 2. Try it yourself. So the midpoint of the second sub-interval is x1 plus x2 divided by 2. Midpoint of the third sub-interval is x2 plus x3 divided by 2. So likewise, you have to explicitly find the midpoints of each sub-intervals using the two endpoints, okay? Just add up the two endpoints and divide it by 2. Right, now we already know the width of the sub-intervals. Width of the sub-intervals is delta x. Now let's find the height of each rectangle. So the height of the rectangle coming from the first sub-interval is that you just evaluate the function at the first midpoint, then evaluate the function at the second midpoint, then you get the height of the second rectangle. To get the height of the third rectangle, evaluate the function at the third midpoint. Likewise, evaluate the function at the final midpoint to get the height of the final rectangle. Now then, what is the formula? So to approximate the integral using the midpoint rule, the formula is, let's find out the area of each rectangle. Area of the first rectangle, the first height times the width, plus the second height times the width. Likewise, this goes on. Let me find some space. And the final rectangle, final height times the width. So width is common, we can factor it out. Then basically, the formula for the midpoint approximation is, let me finish the formula and speak again. All right, let me say it again. Right, what is the formula to find, what is the formula for midpoint approximation? Basically, evaluate the function at every midpoint in each sub-interval and add them up and multiply everything by width. Okay, that's the formula. So let me show you a clear, nice version of the formula with blue color. Here we go. This is the midpoint formula. Here's a graphical view. As you can see, this graph meets at the midpoint of each subinterval. Okay, all right, fantastic. All right, anyway, now let's do an example from the midpoint method. Okay, let's see. Let's start with a very simple example. Let's say you want to approximate the integral x square going from 0 to 8 using the midpoint method using 4 rectangles. Where do we start? First, mark that big interval. It's going from 0 to 8 and find the width. Width is 8 minus 0 divided by number of rectangles. So 8 divided by 4 is 2. So the length of each subinterval is 2, right? 2 long. So let's mark the subinterval 0 to 2, 2 to 4, 4 to 6, and 6 to 8. Okay. Now, what you have to do, what's different from the left endpoint and right endpoint method here is that you have to find the midpoint of each subinterval. So what is the midpoint of this subinterval? Well, between 0 and 2, it's 1. Between 2 and 4, it's 3. Between 4 and 6, it's 5. Between 6 and 8, it's 7. Okay, now it's very visible to our eye, right? These numbers are super nice. You can find the midpoint super easily. But here's the thing, if you are not sure how to find the midpoint, just add up the two endpoints and divide it by 2. Look what happened. 0 plus 2 is 2. 2 divided by 2, you get the first midpoint, which is 1. 2 plus 4 is 6. 6 divided by 2, which is 3. 4 plus 6, 10. 10 divided by 2 is 5. 6 plus 8 is 14. 14 divided by 2 is 7. So that way you can find the midpoints. Okay. All right. Just in case if your end intervals are not too nice. All right. Now let's use the formula. So what is the formula says? Well, evaluate the function at each midpoint. Okay, so function evaluated at 1 plus function evaluated at 3 plus function evaluated at 5 plus function evaluated at 7 and multiply everything by width. Width is what? 2. Let's evaluate the function at these points. So function is what? X square, if I remember correctly. Yes, it's x square. So here 1 square, here 3 square, here 5 square, here 7 square times 2. 1 square is 1, 3 square is 9, 5 square is 25, 7 square is 49 times 2. 1 plus 9 is 10, here 35, 49 plus 35 is 84, 84 times 2 is 168. Okay, so the approximated value for this integral is 168. That's how we use the midpoint rule. The only difference is that you have to find those midpoints explicitly. Okay, let me show you another example, a worked example, just to make sure you and me are on the same page. All right, here's the example. The example problem is you have to solve this integral. Going from 0 to 1, the function is e to the x square. You have to use 10 rectangles. First, find the width. So 1 minus 0, b minus a, divide by 10, you get the width to be 0.1. Then find all those subintervals. So it's between 0 and 1. The subintervals are 0, 0.1, 0.2, 0.3. So likewise, the main subintervals. Okay, so here I have the list of main subintervals. Now what I did is I made a table. So for each subinterval, I found the midpoint. See? Between 0 and 0.1, the midpoint is 0.05. Now here's where you can use the formula to find the midpoint. 0 plus 0.1 divided by 2 will give you the midpoint. So 0.1 divided by 2 is 0.05. So that's how you find the midpoint. Okay. Likewise, find the list of all the midpoints in each subinterval. Okay. Right. Then evaluate e to the x square at those midpoints. That's what I have done in this table. Okay. All right. Now add those values. Okay, add those function values. So basically functions evaluated at midpoint, add everything up, and then the width is 0.1. Multiply everything by 0.1. Here you need a calculator, so that's why I'm not doing this by hand. So if you do that, you get 1.460. Try it out. Okay. So I wanted to again have you use the midpoint rule correctly. Okay. All right, that's it. Well, in the next video let's discuss about the trapezoidal rule. Okay, thank you very much. Bye bye.